We have a solid bar here, and the diameter is 40 millimeters. We want to find the stress at both A and B, but because they're in that same slice, we're only going to need to find one set of internal loads for these. So stress at A and B. And by stress, I mean that stress element like we drew in the previous problem. Now, they're going to be different because they're located at different places through the cross-section. And the 800 Newton load is being applied through the centroid of the cross-section. All right, so first thing, to find the stresses at A and B, we need to find what the loads are on that plane that we're slicing through. And in this case, we can, again, take a slice through that section and keep everything in front of it. And we don't need to find what the reaction forces are in this case. We can jump right to the internal loads. We're not given a coordinate system, so we can choose one. Well, we are given a coordinate system. I'm actually going to move it. I'm going to center my coordinate system at the cut. It's just going to make it a little bit easier here. I have that external force of 800 newtons. That is 30 degrees from the vertical, which is the z-axis, or the negative z-axis in this case. We call this z, y, and x. And that 800 newton is in the zy plane. Where I made that cut at Q, I'm now going to have my 6 internal loads that are now exposed. So first is the value P coming out from that cut surface. And then immediately I know that my assumption is that T is positive around that axis. So it's going to be around the negative y-axis according to my global coordinate system. And then my shear force is going to be along that cut surface. So a component will be in the z direction, I'll call Vz, and a component in the x direction, Vx. And then like in the last one, I'll have a component of my bending moment around the z-axis and a component around the x-axis. Right, looking at my sums of forces, sums of moment, in the x direction I have Vx. I have no applied force, so I know that my shear force along the x direction is 0. In the y direction, I'll have negative P plus 800 sine 30. So my internal normal force, 400 newtons. And in the z, I have Vz. In the negative z direction, I'll have a minus 800 cosine 30. So my Vz, 690 newtons. If I take the sum of moments around that cut at point Q, I can get my moments this way. I will have mx around the I direction, minus t around the j hat direction, plus mz around the k hat direction. And then I need to use the cross product using R cross F to go from Q to where that force is being applied. I have to go 0.2 meters in the positive y direction to get from Q to where that 800 Newton force is. And then the value of my force will be 0 in the I In the J direction, to save room, it's positive 400. And the K direction, it's negative 690. And this is in newtons. This is just coming from 800 sine 30, negative 800 cosine 30. Okay, I go through all this, and I get my values for mx, which I'll write over here. My mx, I will get 139 Newton meters. mz, I get 0. And t, I also get 0. Based on my original picture, I now want to look head on at the surface of that cut that I made. So I want to look at from behind, so I'm going to be standing on the y-axis, looking in the positive y direction. So I'm going to see x to the right and z up. Again, we're standing on the negative y-axis, looking forward, and we're seeing the surface of this cut now. And in this problem, we are interested in looking at what's the stress state at A and the stress state at B. So again, looking from the vantage point of the negative y-axis, A will be on the extreme right, and B will be at the bottom. And now I can put everything facing the correct directions now, the internal loads I found in the previous step. So for example, Vz was in the positive z direction with 690 newtons. So that will go on my picture in the correct direction. P is 400 newtons, and it is then in the negative y direction. So that will be coming at us. I'll try to illustrate that. So that's going to be coming at us as we look at it. And mx was positive 139, so it was indeed around the positive x-axis. So I'll have that bending moment around the positive x-axis of 139 Newton meters. Again, this is illustrating about the positive x-axis, or you can use a double head arrow. It might be easier to look at that way. But that's my bending moment from the 139 Newton meters. So what I want is a little stress cube on A and a little stress cube on B. Now I'm analyzing what are the stresses acting at each of those points. So while I'm here, I'm going to need to use certainly the value of I, so I might as well calculate it. In this case, pi over 4. My diameter is 40 millimeters, so my radius is going to be 20 millimeters. My moment of inertia is therefore going to be 126 times 10 to the negative 9 meters to the fourth. I also may as well calculate the cross-sectional area, since I'll need that as well. So pi r squared, the cross-sectional area 1.26 times 10 to the negative third meters squared. Right, so now I have to go one by one looking at the loads and seeing what stresses they cause. So in this case, I do have a value for P, so let's look at we can consider kind of both things simultaneously here. P over A is the only one we say is uniform. So that normal stress will affect A and B the same. So the normal stress, 400 over the cross-sectional area, 1.26 times 10 to the negative third. So we'll introduce a normal stress to both of them of 318 kilopascals. Here, the sign on P is important because this will tell us, is it tension or is it compression? Because P was positive, that means that the axial stress is tensile. So on that front face, it's going to be pulling with a value of 318 kilopascals, and it'll have the same effect on A and on B. The 139 Newton meters, how will this affect A? How will this affect B? Right? A is not going to be affected by this because A lies on the neutral axis with respect to that 139 Newton meters. So that will not add any stress to A, but it will to B because it's not located on the neutral axis. In fact, it's at the bottom, so it's maximally affected by this 139. Right, and we know ahead of time exactly that B is going to be in compression because of the way this is. It's going to be pulling out everything above the neutral axis and pushing in everything below the neutral axis. So we know it, only B is affected and it will be compressive on point B. And we know then the value will be my over I. We're in Newton meters here, so that's the correct units. Y is just our distance from the neutral axis that we're bending about. In that case, we are located 20 millimeters away from that, or 20 times 10 to the negative third meters. And the value of I we already calculated, 126 times 10 to the negative 9 meters to the fourth. So we get, again, a compressive stress on B with a value of 22.1 megapascals. So A, we don't add any more stress to. B, we now will superimpose also this stress, a compressive stress now, also on that same plus or minus Y face, 22.1 megapascals. It's compressive, so it's pushing in on those surfaces. And notice when I'm drawing these, I'm not putting ever negative numbers when I draw these. I'm just making sure the arrows point in the right direction. So it's 22.1 megapascals, but pushing into the surfaces. This was 318 kilopascals pulling out on those two surfaces. And again, A doesn't get affected by this. Right? The bending stress is taken care of. It only affected B. It didn't affect A. And then finally, we have the shear force, the 690 newtons. Now, again, we are considering both A and B. Which one will be affected by the 690? Which one will not be affected by the 690? Right. A will be. It's on the neutral axis, and we know that shear stress is transverse shear stress is maximized there. Will B be affected by the 690 Newton shear force? No, because with respect to this neutral axis, it's at the bottom of the beam, or it's at the bottom of the cross section. So B will not get a shear force, but A will get a shear force. So only A is affected here. So B we're actually done with, but we'll hold off until the end, summing everything. At A, we'll have VQ over IB. 690 newtons. I is 126 times 10 to the negative 9. A is located at the neutral axis, so when we make our mini shape, again, everything above or everything below. We're cutting through the entire diameter here, so the diameter is our value of B, 40 millimeters, or 40 times 10 to the negative third meters. And we have to calculate Q. Well, we know that this is a half circle, so we know its area is going to be pi r squared over 2. And we know that this distance here is 4r over 3 pi. So if we multiply that area by 4r over 3 pi, we're going to get a Q value. I won't go through all the intermediary steps, but Q will get 5.35 times 10 to the negative 6 meters cubed. We get 730 kilopascals. B does not get affected by this. So how do I illustrate this shear stress on the cube at A? Right? It's going to be in the same direction on that front face as the shear force. So it's up. And because it has to be in equilibrium, I now know the directions of the other shear force, shear stresses on it have to meet in the corners. So on the bottom, we'd be going back. On the back side, we'd be going down. So really, we can only see the front and the top from this picture. The front goes up, the top goes forward, the back goes down, the bottom goes back. Again, 730 kilopascals. Final step, putting it all together. My stress state A, I'll keep it oriented the same way that I have. I have a tensile force from the axial stress. I have a shear stress from the internal shear force. This is a normal stress, this is a shear stress. So I just superimpose them. They're not going to affect each other. So I just have them happening at the same time. So on that positive and negative y faces, I have 318 kilopascals of stress. And on the front, back, top, and bottom face, I have 730 kilopascals. Then at B, I have no shear stresses acting at B. I have a tensile stress and a compressive stress. Now they won't be, they'll add together, but now they're going in opposite directions, so I have to take that into account. So what I have to do is I have to take I can do it in two ways. I could say I have plus 318 kilopascals minus 22.1 megapascals is going to result in a negative stress, which is a compressive stress. So in total, I'll have 21.8 megapascals of compressive stress.